Testing. Okay. Oh. Now? Okay. Talking. Hello, everyone. Can you hear me? Seems not very clear. Is this better? Okay. Yeah, hello, everyone. Welcome back to our tutorial, Differential Privacy in the Wild. So in the first half of this tutorial, we already covered the intuition and essential concepts of differential privacy, and also see how to answer queries on table data. And in the second half of this tutorial, we'll focus on real-world settings that involve complex applications such as machine learning algorithms, and also complex data types that beyond table data. Hence, in those settings, we only see theoretical challenges, also practical challenges in defining what privacy notion to use and designing algorithms. So in these following 3 modules, we're trying to address those challenges. Let's first come to one of the very important application problems, machine learning. There's a rising number of applications in the domain such as advertising, medicine, genomics that use machine learning algorithms on sensitive data collected from individuals. Hence, it's very important for us to design differential private machine learning algorithms. So in this module, we'll first cover 2 groups of machine learning algorithms. First, we're using empirical risk minimization as an example to show how to make a specific learning approach private. You only see empirical risk minimization in SVM and logic regression. And the second group of differential private algorithm, we use stochastic gradient descent as an example to show how to make a general purpose fitting techniques private. Besides these 2 groups of algorithms, we'll cover other important problems in private learning. So first, this is a very simple but real-world example to show machine learning problems. And here, we want to come out with a predictor to predict whether a person has a flu or not based on the symptoms. And this predictor is trained actually on sensitive data of the patients. So these machine learning algorithms can be simplified into this format. So the attribute data can be mapped to a label data, which consists the features of the patients, whether they have flu, they have fever, what the temperature is, and correspondingly have their label, which indicate whether this person has flu or not. And based on this private data, we like to build a public classifier to classify whether a person with certain features is belong to their positive, has the positive label or the negative label. And here's an example that we can find a vector to separate the positive examples from the negative examples. And those examples are drawn from R2 distribution. More formally, we can formalize these problems as empirical risk minimization. So given this training data that consists X and Y for each record, and Xi other attributes, features, for example, the symptoms of the patients, and the Yi are the labels. If the Y is -1 and +1, this belongs to a binary classification. And we like to train a predictor based on these set of examples. And how well this predictor works, we can empirically measure by the average error made by the predictor over the entire training data sets. And the error made by the predictor for each example is measured by the loss function, L, which is presented by here, L. Here are 2 examples for loss function. For support vector machines can use hinge loss, and logistic regression use logistic loss function. Besides minimizing the risk or the training error made by the predictor, want to try to control the complexity of the model as well. Hence, we usually, in the objective function, we're including a regularizer, which to prevent overfitting of the data. And why do we need differential privacy? We use our support vector machines example. So support vector machines solution is a combination of support vectors, which is highlighted by the circle here. If one of the support vector moves, let's say the vector or the red vector moves, and the solution will changes, right? So this actually likes the presence, the absence of certain example in the data set. So the first group-specific algorithm, we're going to use ENR as example to show how to ensure differential privacy of this type of algorithms. So rather release our exact solution for ERN, we can sample a solution from a distribution that close to the optimal solution. And one way to achieve this is to add in noise to the output of this optimization problem. So first, you find the solution, the optimal solution to this problem, and then you add in noise. And the amount of noise you added to this problem, as probably you have seen before, is going to be proportional to the sensitivity of the solution. And the prior work has shown that the sensitivity of this solution can be bounded by 2 over lambda n, as long as the loss function have certain property, convex property. And lambda here is the parameter for the regularizer, and n is the number of the data points in the training data sets. Given this L2 sensitivity, you can add a noise, and this noise can be drawn from the gamma distribution, that the variance depends on the L2 sensitivity, and the direction can be drawn uniformly at random. So there are some issues for this output perturbation algorithm, considering for real data sets, it's possible that their optimization surface is very stiff in a certain direction. So imagine you perturb the solution in that direction, the objective value will incur a high loss, right? So there's another different approach that instead of injecting noise to the output, you're adding noise to their objective function. In other words, you can perturb the optimization surface. So the idea for this approach is that adding noise is part of the computation. So you already add the regularizer to prevent overfitting. So why not adding additional noise to ensure privacy? And similarly, noise can be drawn from gamma distribution, but the variance of this noise is no longer independent on the sensitivity. The prior work shows that as long as their loss function is convex and double differentiable and smooth, and the algorithm can satisfy differential privacy. And compare these two approach, objective perturbation and output perturbation with respect to their non-private SVM. And the accuracy is measured by the number of samples to achieve certain accuracy or error indicated by their alpha here. So you can see that the number of samples required for both perturbation method requires additional samples to achieve the same accuracy. And particularly, the output perturbation requires additional number of samples with a factor of 1 over alpha, square root alpha. And also practically, when we run experiments, we show output perturbation gives more errors than objective perturbation method. Okay. So already see our example to show how to make a learning problem approach private using empirical risk minimization. So usually for this group of algorithm, you assume an exact full solution of the optimization problem can be found. But this is not necessarily true in real-world application, especially scalable systems. There's another approach people use. They use their fitting techniques to search our optimal solution to approximate the true solution, given limit of time. So one example for such fitting techniques is stochastic gradient descent. We have seen that people apply differential privacy on these fitting techniques in the application of deep learning recently. At a high level, these techniques are following this way. So first, you initiate the solution with some value, and then you update this solution with a random sample from the training data set, xt and yt at time t. And the solution is updated by reducing in the direction of the current solution and at xt and yt with a step size alpha t. And the order of this random sample can be based on a random permutation of the training data sets at the beginning of each pass of this stochastic gradient descent method. And if you use this permutation, this algorithm can be known as perturbation-based SGD or PSGD. So if you cycle these data sets k times, this is called k-pass PSGD. So how to make these techniques differential private? Okay, so similarly, you can add in noise to the solution at every iteration. Because this is a white box approach, because you actually modify the code of SGD, right? And what is the privacy guarantee for this approach? Suppose the data is cycled k times, and the basic composition actually says that the k pass of this algorithm is k times epsilon differential private. And we can see that the privacy loss actually increases as the number of passes increases. And usually the algorithm SGD requires the number of passes to reach convergence. So which is not very nice. However, in more recent work, people apply advanced composition techniques to tighten the bound of this privacy loss. And they apply these techniques over problems that dealing with the convex objectives or so non-convex objectives. And the high-level intuition for advanced composition is that composing K algorithms and each of them satisfy epsilon differential privacy, or they satisfy epsilon G differential privacy with high probability. So this is not the definition for pure differential privacy, but a more relaxed version, which is called epsilon delta differential privacy, where the epsilon here is in the order of epsilon times square root of k log 1 over delta plus k epsilon square. So this privacy bound is much tighter than k times epsilon when k is large and epsilon is small. So how do we get this result? It's by analyzing privacy loss actually as a random variable. So we define this random variable for given output and neighboring database D and D prime is the log ratio between the probability to generate output O from D and D prime. And if the algorithm is epsilon differential private, what does it say about this random variable? It says this random variable at the worst case lies between the value from negative epsilon to epsilon with probability 1, right? And similarly, as this is a random variable, you also can analyze the expectation or variance of this variable. And then we can bound the sum of these k variables with the expression we see above with a high probability 1 minus delta by Azuma's inequality. Okay, so in this way, we can get a tighter bound for composing k differential private algorithms for machine learning problems. And however, as we see, for this white box approach, you need to add in noise to every iterations, and you need to modify the code, and it only can satisfy epsilon delta differential privacy, which is a relaxed version differential privacy. So a more recent work proposed a black box approach. Doesn't mean that it doesn't know what's happening inside the algorithm. You still know that, but you just don't have to modify the code. And only need to sample the noise once and add the noise to their final output. And this algorithm satisfies epsilon differential privacy. And at the same time, given a constant number of passes over the data, you can obtain a better convergence. And actually, the paper that discuss This approach will be happening on Thursday. It's called Vote on Differential Privacy in the DP session. Okay. And the high-level ideas, they come out with their L2 sensitivity of these whole K-pass PSGD algorithms. And under certain convexity conditions, the L2 sensitivity can be bounded easily. And then adding a corresponding noise to their final output will guarantee the whole process is differentially private. And when the number of passes over the dataset is constant, they have shown this black box approach can have a better convergence than the private work that adding noise to every iteration. So for convex loss function, the improvement is about a factor of log 3 over 2n. And for strongly convex loss function, the improvement is about square root d and log n. So remember, this is for constant number of passes. So for white box approach, when you're adding noise to every iteration, usually they consider a number of passes that is order of n, which is similar to the data size. So when that happens, the denominator of the bound will go to n and n squared for convex and strongly convex loss function. In that case, the algorithm, the white box approach, will be having better dependence on the data size. Okay, so there are other fitting techniques. So in the previous approach, we see every iteration you take just one example, and that is very similar to a local perturbation of the record. And instead of doing that, we can actually process a batch of examples per iteration and adding noise to the average direction at that point. So both white box approach by adding noise per iteration and adding noise to the final output can be applied here. Another fitting technique is called proximal algorithms, also designed for strongly convex optimization. For that piece of work, they adding noise per iteration. There's no analysis on the L2 sensitivity, and it's harder to implement than the stochastic gradient descent method. Okay. So we have covered two groups of machine learning algorithms. And last one, other important problems in private learning. One issue is similar is that many tabular data problems are in machine learning problems. We need to tune the parameter or select what is the right models. Your exponential mechanisms apply here. How to deal with another problem is how to deal with high dimensional data. In one of the work, they apply random projections to project their high dimensional data to low dimensional. And another important problem is how to solve non-convex optimizations. One of the most recent work apply differentially private stochastic gradient descents for deep learning, but there's no theoretical results. And how about other applications, whether they can work really well? It's an interesting question. And another line of theoretical work that really explore what the limits for what can be learned privately. They also draw a link with the learning theory that covers pack learning and statistical query. And they also mention what cannot be learned privately. The examples they give is threshold functions, where the hypothesis for space for that problem is actually infinite. Okay. So in summary, we covered these two groups of algorithms, differential private algorithms for machine learning. The first group is to make a specific learning approach private. There are two ways to do that. One is perturb the output. One way is to perturb the objective. And the second group of techniques is to make our fitting techniques differentially private. We use SGD as an example. So there's a white box approach, adding noise to every iteration, and a black box approach, where you're adding noise to their final output. So there are more interesting algorithms coming on, especially for example, non-convex optimization problems. So hopefully, this is clear. If you have any questions, I'm happy to answer them. Okay. Otherwise, we'll move on to our module 5.
Okay, so we now move on to the next part. So we're going to talk a little bit about, so we talked a lot about sort of the theory and the algorithm design that goes on behind differentially private algorithms, right? So one question that you can ask, and most people ask, is, does this stuff really work, right? Because you are trying to answer queries, or you're trying to sort of do machine learning, but you have to add noise, right? And like in real situations, are we adding a little bit of noise, adding a lot of noise? How does this actually work, right? So in this part, I'm going to talk about, first I'm going to talk about a couple of real-world deployments of differential privacy. It's 10 years since this idea was introduced, and there have been a few sort of deployments of differential privacy. I'm going to talk about two of the significant ones. And until now, we've been really talking about data that sort of fit in a single table, right? And you have these rows, and you can think of each row to be an individual. But in the real world, when you look at sort of real applications, data doesn't sit in a single table, right? You have more complex structures. So we'll talk about privacy beyond tabular data, okay? All right. So the first real-world deployment I'm going to talk about is from the US Census Bureau. So the US Census Bureau releases a lot of data products. They basically collect information from individuals, and they also collect information from sort of establishments, like businesses, okay? And they create a large number of products which are aggregated statistical data sets that are then released, and those are used for policy making, those are used for economics, and so on. So one of the applications is called On the Map. So what On the Map does is it actually takes the US map and divides it into small geographical regions called census blocks. Okay, each census block is like a few buildings. So it's really, really very identifying. Okay, and in those census blocks, it actually tries to release how many people work at a business at businesses located in that block, and where those people who work there, where do they live? And they're cross-tabulated by the characteristics of the businesses and the characteristics of the individuals and so on. Okay, so they want to release this data set. Okay, so I mean, to think like a database person, it's basically two tables, two kinds of entities. There are employees, there are employers, and their attributes. And there's a link table with this job, which is basically which employer works at which employee works at which employer. Okay, so this is the data set that they have. Now, why do they want to release this data set? There are many reasons. So one of the applications is actually there online, which is live, is called On the Map for emergency management. So what they do there is, if, for example, they track a hurricane, say Hurricane Sandy, which hit New Jersey, and they can, based on the data, they can tell how many jobs and how many individuals are affected by the hurricane, right? And based on those numbers, the federal government, for instance, calculates how much assistance has to be given to various counties in the United States, right? So it's good, you have to get this right? If you had a lot of noise, then you will be giving aid to the wrong counties, right? So therefore, having accuracy is extremely important, right? But at the same time, privacy is extremely important too. It's actually more important than most applications because it's written in the law, okay? So there's this code, US Code Title 13, Section 9, which basically says that it's against the law to make any release of data where the properties of a particular establishment or the presence of a specific individual can be identified from this release. Okay, so you cannot re-identify an individual. You're not allowed to learn specific properties of establishments either, right? And not only that, violating this statutory confidential pledge can result in fines. In fact, for every individual that gets re-identified, the people who are in charge of this release can be fined up to $250,000 and potential imprisonment up to 5 years. So it's a huge deterrent, right? It's a matter of criminal law. Okay, so therefore, you have to satisfy privacy. Okay, so what is this data set, right? What is this data set? So you can basically simplify this data set as essentially trying to release counts of people who work in a specific place and live in a specific place, right? So there's origins and destinations, and there are these worker IDs, And basically, you know where businesses are located, right? Because that's a physical location. You know where they are. And what is sensitive is the residences of these individuals, right? And each of these are census blocks. And what you want to release are the counts of, for every origin-destination pair, how many individuals live in that block and work in the next block. Right? That's the problem. So this is something, this is not new. They've been doing this for a long time, right? So they already have some existing approaches. Their existing approach is to build a synthetic database. And remember, synthetic database is basically you add noise once and you release it, right? And so the way and the nice thing is that you don't need to maintain the history of queries, because once you create the synthetic database, you can just sort of work with it, right? And the way they did it was to, circa 2007, was basically to take the table, existing table, and basically run a group by count, like number of workers who live in one place and work in another place. And to each of those, they add some noise using some method, okay? And then they took it this noisy thing as a model, and then they do some sort of sampling called Dirichlet sampling to sample new synthetic fake people from there. Okay? While I'm not going to go into the details here, the main point here was that if a specific origin destination pair did not appear in the table, that is, there was no person who lived in some block and worked in some block, that's count was 0, then they did not add noise to it. Okay? But basically, because they didn't add noise to those origin destination blocks that did not appear in the true data set, you can actually create re-identification attacks. Right? So remember those deterministic algorithms that Michael showed, where you could have some probability of going from one input to one output to become 0, and that violates differential privacy. So those kind of situations can also lead to re-identification attacks. Right? So therefore, this existing algorithm was sort of does not provably guarantee privacy of any form. So in a 2008 paper, researchers sort of figured out how to make it differentially private. And the high-level ideas was basically you have to add noise to all pairs of origins and destination blocks, okay, even if the count was 0. And to sort of ensure that you actually get useful data out, the noise is calibrated so that you get a weaker notion of differential privacy, where you allow for some probability of failure. And utility was also improved by sort of coarsening the domain and sort of dropping some blocks. But sort of to sort of show visually what they got, so this is an example of an experiment that they ran where they looked at, for every block, they plotted the average commute distance of individuals. And they wanted that distribution to sort of be preserved. So in this plot, the red points are points that are coming from the original data set, and the blue crosses are points that are coming from the noisy data set that is generated from the differential private algorithm. And this was done with an epsilon of 8.3 and with a small probability of failure of 10 to the minus 5. And at this epsilon level, they actually got some the distribution sort of matched. They're very, very similar. And this is the algorithm that is actually being used currently by the US Census Bureau to release this data. Okay? So there's one sort of real deployment of differential privacy. Okay? All right. The second deployment of differential privacy is in the Chrome browser, okay, by Google. Okay? So Chrome has this dilemma. So cloud services in general want to protect their users, want to ensure the security of their users. Okay? And and they want to secure the service itself from abuse. So what is the problem with what is the security issues in a browser, right? Like a malicious piece of code could come and say hijack the browser, like change its settings, change its search page, change its home page, right? And alter the behavior in which the browser works, and thus affect how the users interact with the web, right? So for instance, Chrome wants to monitor such statistics so that they can detect an attack early, right? So for example, they want to monitor did a large number of users have their home page redirected to a malicious page in the last few hours, right? Or in the last day, or in the last 2 days. But users don't want to give up that information, right? I mean, the reason is that things like the browser configuration are extremely identifying. So in fact, you can construct what is known as a fingerprint for a browser, which includes things like your homepage, the kind of plugins it has. In fact, based on using the browser, you can actually detect what kind of hardware cards are there on your display devices. By displaying certain graphics, you can figure out which graphics card you're using. Right? So you can construct a detailed fingerprint of your browser, and there are sites called like panopticon.com where you can actually go and you can check how unique your browser is. And usually your browser is unique up to 1 in like 500 or 1 in 100. Right? So browsers are pretty unique. And if you have such a unique browser fingerprint, then you don't need cookies, you don't need anything. You can just use the browser fingerprint to uniquely identify you and track your browser history. Right? So it's very sensitive information that users don't want to give up. And in fact, Google doesn't want to keep this information too, which I'll come to in a few slides. So the problem basically that these guys are trying to solve is that you want to learn patterns of changes in browser characteristics. So for example, what are frequent unexpected Chrome homepage domains, right? Without while guaranteeing the privacy of each individual, right? And in this case, there's a liability for Google to actually collect the true information from all the respondents, right? Because if Google collects all the browser fingerprints, and tomorrow if the US government comes and says, give me that data through a subpoena, they are forced to give it, right? And then the government can actually track you, right? So they don't want that liability, right? So therefore, this gets into a situation where you want to be in an untrusted server setting where each of the respondents actually perturb their information before giving it up to the server. Okay? So how do you solve this problem? And we sort of saw this before, right? You can perturb each record, right? And you can solve it using this randomized response technique that Michael talked about, right? Which is, if you have a binary value, then with probability p, you report your true value. With probability 1 minus p, you report the false value. And as long as p over 1 minus p is bounded by e to the epsilon, you get differential privacy, right? But we don't have a binary value here because Chrome is trying to figure out which URLs, which homepage domains did the browsers change to, right? And that's not binary domain. That's a huge domain, actually. And in fact, as the domain size increases, this probability that the original value is reported becomes extremely small, that you get no signal with this perturbation, right? So a solution that the Google Chrome guys came up with was basically the following. They used first Bloom filters to reduce the domain size. Okay, so rather than having sort of potentially infinite size, they reduced it to say like 256 bits. And you can do that by using multiple hashes in a Bloom filter. And now that you have a Bloom filter, it's basically a bunch of zeros and ones. You can apply randomized response to each bit, right? But of course, if you apply randomized response to each bit, now you have to use sequential composition, right? So if you get epsilon differential privacy for each bit, you have to sort of do those many number of times differential privacy. Okay, so you can now do sort of randomized response in each of the Bloom filter bits. Additionally, in this solution, they actually did a second round of randomized response on this fake Bloom filter itself. The reason they did that was they wanted to collect information over multiple days. And if you did randomized response only once, then you would be able to track an individual based on this fake Bloom filter. So they did this second level of randomized response so that you can't track an individual using these solutions. And then finally, they used all of these noisy Bloom filters, and they added them up and did a little bit of inference to reconstruct the actual values that they wanted, which was how many times a specific domain was the home page for how many users a specific domain was the home page of those users, right? And based on that, they can actually construct such histograms for basically, given these are the URLs, how many users had this as their homepage. And they could get pretty good accuracy for a large number, as long as the number of clients is very, very large, which is true because number of Chrome users is very large. Okay. So there have also been a few other real-world developments, a handful really. For example, Yahoo data was used to release sort of frequency lists of passwords in a differentially private manner. There's some work from AT&T where there's a system for releasing mobility traces. under differential privacy. And Apple has had a sort of major publicity splash saying that they're going to use differential privacy in their Apple Watches. And you can actually, in the latest iOS update, it actually tells you what kind of noise is added and so on. Okay. But in general, the number of deployments of differential privacy is not very high. It's been pretty hard to sort of deploy differential privacy to the real world. I'll talk about one of the causes now, and then Michael will sort of talk a little more about it later on. Okay. So before I move on, any questions at this point of time? All right. So one of the challenges in applying differential privacy to the real world is that differential privacy makes this assumption that the data is like a table, right? In fact, the definition of differential privacy itself is like you have two databases that differ in one record, right? And if the record is an individual, it makes sense. You're saying, oh, I can't tell whether the record is in or out of the table. That's what the meaning of the two databases that differ in one record is, right? But in general, what does a record mean, right? So let's talk a little bit about that. So what is a record? How do you define these neighboring databases when you have more complex data types? Okay, and that will lead to another problem, which is that these records can be correlated, and I'll talk a little bit about that as well. So let's first talk about the first non-tabular data set that you can think of, graphs, like social networks, right? A lot of data can be succinctly represented as a social network. And here in a graph, you can think about different kinds of neighboring databases, right? Two graphs can differ in the presence or absence of an edge. So your record could be an edge, right? Or the record could be the friend list of a single node, the entire adjacency list of a node, right? So depending on how you represent it, either a set of edges, a record is an edge, or if you represent it as a matrix, right? And the row of a matrix is basically the entire adjacency list of an individual. You could differ in either of those two, right? In both these cases, what does privacy mean? Is one better than the other, right? Another example is in trajectories, right? So what is a trajectory? For example, your cell phone can track through your GPS or your Wi-Fi your location at any point of time, right? So over time, you get a trajectory of locations that this individual went through, right? So in this case, what is a record? Is a record a single location at a single point of time for the individual? Or is it sort of a sequence of locations spanning a window of time? Or is it the entire trajectory itself, right? As a third example, let's come back to this US Census Bureau example, right, that we talked about, this on-the-map thing. Well, you have two kinds of entities here. You have employees and employers, right? And both of them have to have some privacy protection, right? So what's your neighboring database here? Is it like, is a record an employee? Is a record an employer? Is it something else? Right? Actually, this is something that we tackled in a talk on Thursday in the differential privacy session at 2 p.m. Okay, so this is one challenge with differential privacy. Everything is sort of record-based, and in this complex data sets, what does a record mean, right? And the second problem is that records in a data set can be correlated, and this is a very subtle problem. So let me explain it with an example. So let's say I'm in this fictitious world where there are two kinds of people. There are these blue community of, I don't know, mathematicians and green community of physicists. Okay, and they don't want to disclose the fact that any single mathematician is actually, you know, collaborating with a physicist, right? So therefore, you should not disclose the presence or absence of a single sort of Bob Alice edge, right? But at the same time, they want to show the world, you know, that there is a lot of collaboration between them. So they do want to release like the total number of edges between these two communities. Okay, so if you think about it, I mean, if I want to protect each single edge, and I want to release the total number of edges, I mean, if I add or remove an edge, then the sensitivity of a count is just 1, right? So I can just add Laplace, take the true count, add Laplace noise with parameter 1 over epsilon, and I get a differential private count, and it should all be fine, right? That should hide the presence of this Bob Alice edge. Well, let's see a little more, right? It's not necessarily that is the case. So let's say there's an adversary who actually knew something about how these social networks evolved over time. And let's say the adversary knew the point of time, knew the structure of these networks at the point of time when this Bob Alice edge was created. right? So he can run this thought experiment. Let's consider one case where the Bob Alice edge was not there, and another time where the Bob Alice edge was there, right? And you could say, now let me grow this using a social network evolution model. And there are many social network evolution models, like preferential attachment, and so on, right? And in fact, if you do this, right, if you do this, and if it turns out that before the Bob Alice edge was created, there was no interaction between these two subcommunities, what would happen is that in the first case, there would be very few edges between the two communities. In the second case, there will be lots and lots of edges between the two communities, right? In fact, the difference between these edges could be linear or even super linear in the size of the network, right? And now what did you do? What did we do to hide privacy, right? We just added noise that was sort of a constant variance, right? Sensitivity 1. So therefore, in this case, you would get D1 plus some small noise. Here you would get D2 plus small noise, but the noise is only constant in the size of the network, whereas the difference between D1 and D2 is sort of very large. It's linear in the size of the network. So therefore, an adversary can actually distinguish between these two cases. So he can learn actually whether D1 is in the data set or D2, whether Bob Alice edge was or was not present at that point of time, right? So what's happening here is that there are the records in a data set are actually having correlations between each other, and the presence or absence of a record can affect the presence or absence of other records in the data set. So adding or removing a record does not only change the function output by 1, but it could change it by significantly larger number, right? Another way to look at it is basically that if you have sort of a space of all possible tables, right? What differential privacy says is that there are these neighboring tables, which are these tables that are by edges. And for those neighboring tables, I'm sort of ensuring that there's not too much difference, right, in the probability with which an output is generated. But then when you have sort of correlations or certain kinds of background knowledge, some of those tables become either very improbable or completely not possible, right? And so then your differential privacy seems to be giving some sort of a vacuous guarantee there, right? And so but the adversary now, if you look at in this new space, if you construct these sort of neighboring tables, the adversary can actually distinguish between these pairs of tables, and so that's the reason for the privacy breach. Okay, so this is not a problem with differential privacy alone. So this may seem like an attack on differential privacy, but in fact, you can show a more general theorem called the no free lunch theorem, which says that it is not possible to guarantee any utility in addition to privacy without actually making assumptions about what kinds of correlations are there in the data, how the data were generated, or equivalently, what background knowledge the adversary has about the data itself, right? So to give you a very, very simple example, let's say the adversary knew that there's a hospital and all the patients in the hospital either have cancer or all the patients have diabetes. Leaking even like one bit of information leaks everything about all the individuals in the data set, right? So therefore, if you don't make assumptions about what the attacker knows, you can't really guarantee both privacy and utility, okay? So therefore, we need a more formal theory to understand what privacy means and what privacy is actually ensured by differential privacy, both to understand how to extend it to situations where it's not just tabular data with records, but also to understand what happens when you have correlations and so on, right? And one way to do that is using this framework called the puffer-fish framework. Okay, so before I talk about any questions about the no free lunch theorem. All right, so let's talk about this. So the idea behind the puffer-fish framework is the following. So rather than defining privacy just in terms of sort of neighboring databases that differ in a record, what pufferfish does is it asks 3 questions. What is being kept secret? Who the adversaries are? And based on that, it defines information disclosure for the secrets and the adversaries. Okay? So let me explain this carefully. So first of all, pufferfish has this concept of secrets. So secrets are basically any sort of propositional statement, Boolean statement on the data set. So it could be individual specific. So it could be like the individual's record is not in the data set, or the individual's record is in the data set and its value is cancer, right? Or it could be things about groups of individuals, right? These set of individuals, all of them have cancer. Okay, so it could be an arbitrary Boolean statement. Okay, and it defines a set of discriminative pairs of secrets. So these are mutually exclusive pairs of secrets that an attacker should not be able to tell apart. Okay, so for instance, it could be that Bob is in the table or Bob is not in the table. Okay, or Bob has cancer versus Bob has diabetes. And you can define a set of these discriminative secrets, and the adversary should not be able to tell apart any of these pairs of secrets. Okay. Next, Pufferfish tries to define what the adversaries are. Okay. So here, adversaries are assumed to be sort of Bayesian adversaries who are completely characterized by their prior distribution, prior knowledge about the database. Okay. There are no computational limits. So what does this mean? So this is defined by a set of data evolution scenarios. These are a set of all probability distributions that could have generated the data. So think of them as an adversaries prior. So one example is you say that you make no assumptions of the adversary, which means that you consider all possible probability distributions over data instances. Okay. Another example is you have an IID adversary, which is the adversary assumes that the data is drawn independent. Each record is drawn independently from the same distribution, but there's one adversary for every possible distribution of that sort. Okay, and the goal is now to protect every discriminative pair from every such adversary. Okay, so information disclosure is the following: a mechanism M satisfies Pufferfish if for every output, just like in differential privacy, for every output, for every pair of secrets, say Bob is in the table, Bob is not in the table, and so on, and for every adversary such that these two secrets are possible, the mechanism, the probability that the mechanism outputs W, given that the S is true under this prior, is bounded by e to the epsilon times the probability the mechanism is true. Mechanism outputs W given S prime is true and under the adversary's prior theta. Okay. So the nice thing about this is that this gives a very nice interpretation of what privacy is, which is that the ratio of the adversary's posterior odds of whether S is true or S prime is true. If S is Bob is in the table and S prime is Bob is not in the table, then the adversary's posterior odds after looking at the output of whether Bob is in the table or Bob is not in the table over the adversary's prior odds of whether Bob is in the table or Bob is not in the table, that ratio is bounded by e to the epsilon. Okay? Right? So any questions? No. All right. So what does this allow us to do, right? This allows us actually to customize privacy now. So you can set up secrets and discriminative pairs based on the requirements of what must be kept secret. So if you have a graph data set and the goal is you should not be able to learn something about an edge, then your secrets can be about edges. Or if you have a graph database and if the properties that you want to keep secret are about sort of degrees of nodes, then the secrets can be degrees of nodes, right? You can customize your privacy. You can set up your data distributions to capture what correlations are known to the adversary, right? And then Pufferfish results in a privacy definition that bounds the adversary's posterior and prior odds for every discriminative pair. Okay, in some sense, it gives us semantics for what privacy is. And so the advantages of Pufferfish is that essentially, privacy is defined more generally in terms of customized secrets rather than records. In fact, it allows you to better capture legal privacy policies. It actually allows you to better explore the privacy utility trade-off because you have more knobs now to control the trade-off between privacy and utility. Before, in differential privacy, you just had this epsilon, right? More epsilon is less privacy and more utility. Less epsilon is more privacy and less utility. But now you can change your secrets, you can change your adversaries, and so on. And so again, we have a talk in Thursday, which actually talks about this. And it actually, the other important advantage is it actually gives a deep understanding of the protection afforded by existing privacy definitions. So let's see what differential privacy means in this Pufferfish lens, right? So you can actually write differential privacy as an instance of pufferfish. Okay, so differential privacy, what does it say? It says I'm looking at pairs of data sets that differ in one record. So what could the secrets be? Well, the secrets could be that you have a pair of secrets of the form record I is not in the database, or record I is in the database and takes some value X, right? And those are the pairs that you're trying to protect. Now, attacker should not be able to tell whether the record is in or out of the database, right? What are the data evolution scenarios? So one way you can write it is to say that you have a bunch of records. Each record has some probability of appearing in the data set with some value, right? And let's say my attackers have all are of the form that they assume that the records are all independent, but they may have an arbitrary prior for each record in the data set. Okay? So it turns out that the mechanism satisfies differential privacy if it satisfies pufferfish instantiated by these set of secret pairs and this kind of attacker who assumes that there are no correlations between records. Okay? So therefore, it sort of gives an explanation of why we had the attack with graphs and adding Laplace mechanism there. Because when you have correlations between records, then even if you have a differentially private algorithm, you can still learn sensitive properties of the data set. Okay? So before I sort of conclude, there are still some challenges with pufferfish. So for instance, setting up data generating distributions are tricky. Like you have to make some assumptions about the adversary. Which assumptions are the right ones? Like why is assuming records independent, is that a valid assumption? If it's not, then what kind of correlation do you assume? That's very tricky. There's also not too much work on algorithm design for pufferfish. That said, there's a very nice talk that's going to happen in the 2 p.m. differential privacy session on Thursday by Shauna, which actually talks about a first generalized mechanism for pufferfish. And finally, not all pufferfish definitions are good. I mean, this is a framework for generating privacy definitions. Differential privacy is one nice privacy definition. It satisfies a lot of desiderata like composition and so on. All pufferfish definitions do satisfy some desiderata, but not all of them are useful in the sense that they give a lot of privacy. So for instance, not all pufferfish definitions actually satisfy composition, which makes it hard to do algorithm design under this. Okay? So to summarize this module, basically you have these complex data types, right, in the real world, which require sort of custom privacy definitions. Differential privacy does not directly apply. And this has been one of the blockers for applying differential privacy type techniques to the real world. Okay, and one way to handle that is to use this kind of pufferfish type mathematical framework to define privacy. Okay, and so in the next module, she is going to talk about specific instantiations of pufferfish in like graphs and trajectories. And before that, are there any questions? All right, let's move on to the next module.
Yeah, thanks very much, Ashwin. So in the previous module, we have seen how pufferfish framework can be very important in dealing with real-world applications. So in this module, we're going to see several non-tabular data privacy definition in the framework of pufferfish framework. Actually, before pufferfish framework, those neighboring definitions already exist. So we would like to see in the framework of pufferfish, how do we get a better understanding of those neighboring definitions? And for other applications, how do we redesign or specify neighboring databases? And that comes to the second part of this module, blowfish privacy. And record that for pufferfish privacy, it can actually specify what are the secrets you want to protect and who are the adversaries, what assumptions can be made for them, and how the information disclosure can be bounded in a similar way of differential privacy. And we probably see there are examples in previous module. For graphs, if you think about the neighbors for graph data, it's defined by two graphs that differ in an edge. What does that mean in pufferfish framework? So you can actually treat the graph is a matrix of bits, and differing in one bit corresponding to whether an edge in the database or not in terms of the secrets. And how about the data generating distribution can assume that all the graphs are possible and every edge is independently present with probability P. And however, we know that this is not a realistic assumption made for graphs because many edges and nodes in the graphs are dependent to each other. And another example we have seen in the previous module is location trajectories. Similarly, a neighboring databases for location trajectories can be in one form that they differ in one location at a particular time of an individual, right? So for this type of neighboring definitions, what does pufferfish means that you treat the whole database or in terms of matrix of locations, and the secret is to protect whether an individual is at a certain location at some point of time. And data generating distribution for these neighboring databases are every location are independent of others. However, again, we know that this is not very realistic assumption made for real-world applications because the current location are very likely depends on the previous locations. So from these two examples, we see that every applications can have different way to specify the secrets and corresponding neighboring databases. And also there are correlations exist in the data that requires further redefine the privacy notions. And for each privacy definitions, you probably need to redesign the algorithms. And there are many important questions. So let's first look at those instances of privacy notion for social network. Our social network usually can be presented as a graph, where the nodes is a set of individuals, and edges is a set of social networks between their individuals. And in the private work, there's a show it's easy to have attacks on a normalized graph to identify the edges, the social links between individuals, or re-identify users in the graphs. Okay? And it's desired to have some differential privacy guarantee over those social network. And the way to define differential privacy for social network is similar for tabular data, except the neighboring database are defined on graphs. So what does that mean for neighboring graphs? One example is we have seen that edge-based differential privacy. The neighbors can be formed by adding and removing an edge in the graph. So the secret here is protect the social links between individuals. And another type of privacy instance is node differential privacy, where you can adding and removing a node and together with other edges in the graphs. So the secret is different from the previous secrets we have seen. The secret here is the presence of the individual in the graph, not. So there are several interesting statistics people would like to learn from the social network. So we'll use one of the example, degree distribution, to illustrate the idea. How do we ensure this query can be answered either differentially private, no differential privately or edge differential privately? So given this graph with 6 nodes, and each node, one node has a degree 5 and 5 nodes have a degree 1. So the table is showing a frequency for those degree values. And this is the degree distribution query. So how do we ensure differential privacy of this query? So a very simple way is to just adding noise that proportional to their sensitivity of this query. But what is the sensitivity under edge differential privacy for this query? So adding or removing an edge from the graph, right? What is the maximum changes to the degree distribution? So when you're removing the edge, 2 nodes are going to be affected. So their degree value is going to be updated to a new value. And hence together, there are 2 times 2 at the most changes to their degree distribution. And how about node differential privacy? So obviously here, when you're removing a node from the graph, all the edges are deleted, right? And how many nodes are going to be affected? So the adjacent nodes that to their delete node is at most n-1. So there are 2 times n-1 degree values that are going to be affected. And in addition to the node that removed, so total together, their degree distribution is going to be affected by at most 2n-1. And this way, if we're adding noise proportional to the sensitivity, too much noise is going to be injected to this query answer. So what is the right way to do this? The key idea for the private work is to project this graph to a theta degree bounded graph. Of course, in the real world, that you doesn't know what is the maximum degree. The maximum degree can be reached to n-1, right? So rather than process the query on the original graph, you process them on our degree bounded graph, and the degree is bounded by theta. And then you can answer the query on the projected graph, and the noise added can be bounded by this parameter theta. And the way to do this projection can be done. There's 3 existing work that I know to do this projection. The first way is to do node-based truncation. So remove all the nodes have a degree that are more than theta. And the second way to have this projection is create Lipschitz extensions. The work for this approach actually reconstruct a bidirectional graph, and then you run max flow algorithms on this new graph. And the flow of the edges can use to estimate the degree distribution. And the third approach is more recent work in last year, SIGMOD, which use our edge-based projection. So it initializes the graph with empty edges, and then insert edges so that the node's degree does not exceed theta. And we see that the sensitivity for these 3 approaches are all bounded by theta. And the last work edge-based projection have a relatively smaller sensitivity, and hence less amount of noise can be ejected to the query answer. But the previous 2 approaches can tackle more than just degree distribution queries. They're available to count edges or small subgraphs. So we have seen several works that on no artificial privacy, as artificial privacy protect have a weaker protection. There are more queries, and study has been done on that. So if you're interested, you can go through their related work. So similarly to social networks, we have no artificial privacy, artificial privacy. Location trajectories also have a rich class of privacy definition can be understood by pufferfish framework. It is well known that location trajectories can be really sensitive. Their individual location data can be highly unique, can easily identify you from the population based on your location patterns, and also very highly predictive, can based on where you have been in the past to predict your future locations. And also the people's awareness about location privacy has increased a lot in the past. Studies show that a geosocial service checking dropped after the user learned that those services collecting that location data. So for location data, there's a rich domain for you to specify what kind of secrets you want to protect. For instance, you want to protect all the properties of this individual at any point in time, or where, for instance, what is the home location of that user? Or you can bind their secrets to just a small window, right? The user visit home in the last hours. And next, that you can just protect the properties of the specific time rather than a window. For instance, whether this person is at workplace or home at a particular time T. And lastly, you can just protect certain properties at that point of time, not necessarily all the properties. For instance, did the user visit someplace near home at time T, but it doesn't have to protect whether he's far away from home. So based on the type of the secrets you can specify to protect, different neighboring definitions can be found. So in the level of protection, the neighboring database definition can be differ in trajectories, window, events, or close by events. Another name for it is joint indistinguishability. So we start from the Wicker's privacy guarantee for location data. So usually joint indistinguishability is applied to the case when only a single location requires protection. So this is commonly seen in location-based service. You want to find a restaurant. So it doesn't want to release the exact location, but a close-by location will be fine. So formally, this definition is defined in a similar way of differential privacy, except the probability to release the same output from the neighboring x and x prime is bounded by e to the power epsilon times r. R is the distance between x and x prime. So the further away these two neighboring databases or locations in this case, the more easy for the adversary to distinguish between them. Okay. However, for standard differential privacy, the term R is not specified. As long as the locations are different, you want the protection to have a ratio raised up to power of epsilon. And that corresponds to the event level differential privacy, where every events have a privacy guarantee to epsilon. And however, these protection can be weak if we know that if the sequence of events are actually correlated. Take example that if a person stays in a location for a long period of time, let's say t, and the overall privacy guarantee to that period of time is going to be epsilon times t. And another way you can say that averaging those approximation of locations can release their real location. So a stronger version to this is proposed a few years ago. It's called W events differential privacy. Rather to ensure epsilon differential privacy for one single event, you can protect the changes within a window of at most W events. So the neighboring definition here is two trajectories that differ in a window at most W events. So the events differential privacy is a special case when W equals to 1. Let's take an example when W equals to 3. So we want to ensure a window of size 3 satisfies epsilon differential privacy. And same for this window. So a naive way to achieve differential privacy for this window base is to split the budget across each event in the window, in this case, epsilon divided by 3, and it easily satisfy our W events differential privacy for this. And the private work proposed some more adaptive way to assign privacy budget within a window. The key idea is they assign more privacy budget to their events have more changes. And if there's very little changes, you just assign a lower privacy budget. As long as the total budget across the window, within the window, is within epsilon, this privacy guarantee is ensured. And a stronger level of privacy guarantee to ensure the whole trajectory is protected. So the neighboring database is D1, D2 that differ in entire trajectories. So this is usually used when we like to release or aggregate statistics about many trajectories. Okay. So now we have already seen several existing neighboring definitions for social network and location trajectories. So we see that for each new privacy policy, a new algorithm has to be designed. How about other neighboring definitions? How do we specify them? So that's why we propose this work below fish privacy. It gives you a way to specify our neighboring databases using a policy graph. It has many nice properties. So first is a special case of powerful fish privacy, and it satisfies sequential composition. And also, you can use a policy graph to specify neighboring database that capture many neighboring databases and other privacy notions you see in Edge for social graphs. And location trajectory can be captured here. And also can handle correlations by constraints that caused by such as private data release or location constraints. And the way to define blowfish privacy is very similar to differential privacy in terms of neighboring database. So the difference is for differential privacy, the neighboring database are formed by deleting and adding a tuple. D1 minus D2 have a size of 1. And for blowfish privacy, the neighboring database are specified by the policy graph, and it can be redefined for every particular applications. So this can be specified by the experts who want to have the domain knowledge. So what is nice about this algorithm, or what is nice about this blowfish privacy is it doesn't have to redesign our algorithm. So one of the prior work on blowfish privacy study are very nice transformational equivalence between blowfish and privacy. So based on this equivalence, it doesn't have to design new algorithms for every new privacy policy, so that you can just answer queries for blowfish privacy by transform the queries to answer the transform queries under differential privacy with equivalent error. And we won't go to the details of here, but there are high-level intuitions that for differential privacy, for every neighboring database, D1, D2 differ 1, have the probability ratio bound by e to the power of epsilon. And then it's equivalent to say that for any pairs of databases, D1, D2, the probability to generate the same output from D1, D2 is bounded by e to the power of epsilon times delta, where delta is the size of the symmetric difference between D1 and D2. And actually, these symmetric difference can be mapped to their blowfish privacy definition, which correspond to their D1, D2, which is their distance metric. Hence, we actually can embed these distance metrics for blowfish privacy into their distance metrics for differential privacy. And that way, the transformation equivalence can be achieved. Okay. And there are several other works also extend differential privacy with metrics, or if you're interested, you can read them. For example, the first work are generalized differential privacy using metrics. But those work can also consider a special instance of pufferfish, but also generalized blowfish privacy using other metrics. And also the second piece of work, which is going to be presented on Thursday, apply the resisting distance as a metrics and compute general sensitivity based on that. Okay. So in summary, we have looked at our different way to specify neighboring database under pufferfish privacy. And there are many interesting open questions. As firstly, how do we identify realistic policy for real-world applications, whether to weaken some privacy notion is acceptable to our users? Also, there's question that how do we design algorithms under more complicated constraints or correlations, as well as seeing that algorithm that designed for dealing with just simply sequential data, that correlations between events or correlations between users for social networks. But however, when those correlations come together, what is the right algorithm to use? And also how to design algorithms that address highly sensitive queries. And last but not least, there's so many algorithms released under different privacy guarantee. What is their overall privacy guarantee for all the release for the same data sets? So that come to the end of this module. Do you have any questions before we get to the summary? Okay, then yeah, Michael will give a summary for the whole tutorial. Thanks.
Thank you, Shi. Okay. Can you hear me okay in the back? Yeah, okay. Yeah, so I just wanted to conclude the tutorial with a brief summary and maybe some high-level sort of takeaway ideas. So I'll do a very brief recap of some of the things we talked about in the tutorial. I thought I could touch on kind of 5 ideas that seem to cross-cut the different applications and techniques that we talked about today. And then I'll conclude with a few challenges. Okay, so just to recap the tutorial, so we're looking at statistical database privacy, right, where the problem is to release aggregates while not disclosing information about individuals. And Ashwin started by enumerating some desiderata in terms of privacy. So we want resilience to background knowledge that the attacker may have that they could use to attack whatever published data we release. We want composition, so we want to be able to execute multiple algorithms on the data and be able to reason about the cumulative privacy risk of running those algorithms. And then we want to avoid privacy by obscurity. So, you know, much in the same way that security by obscurity is a risky proposition, you know, we'd like the differentially private algorithms that are developed to be, you know, publicly available, and the implementations can be inspected, and any bugs can be found out, right? We're relying on the mathematics for the privacy and not just hiding what we're doing with the data. And there are some utility desiderata. So we, of course, want the released information to be accurate as much as possible within the privacy constraints. And I also added useful. And by that, I mean that for the particular application, some of these techniques may or may not be that easy to apply, right? So ultimately, we want tools that for the people, the data practitioners who have the data and who are using these tools, to be able to use them in a way that's easy and works with their current workflow around their data. Okay. So we talked about a variety of applications. So we looked at techniques for answering workloads of queries over tabular data. She talked about machine learning techniques and how you can make them differentially private. We looked at various analysis tasks that you might do on social network data or other kinds of data that can be represented by a graph, and trajectories. Ashwin briefly touched on some real-world deployments of differentially private systems. So at the US Census Bureau, they have the On the Map data product that's releasing commuting patterns. And then Google's Rapport is releasing aggregate statistics about browser configurations. And we also saw several formal privacy definitions, starting with differential privacy and then pufferfish as well as blowfish. Okay, so on to some cross-cutting ideas. So these are just kind of 5 ideas that seem to apply to a lot of the different algorithmic techniques that have been developed. So the first one is that you can often achieve higher accuracy through careful composition, okay? So we saw examples where parallel composition could be used. So with the query answering problem of answering range queries over the spatial data, we saw that by binning the grid into cells, you can use parallel composition across the cells. We also saw with the quad tree approach, you can use parallel composition across the children within the quad tree structure. There's more advanced composition techniques. So she talked about with the gradient descent algorithm that actually looking at privacy risk as a random variable and then trying to bound how far deviations of that random variable and coming up with a more sophisticated composition technique. And there's been actually a lot of theoretical work on advanced composition techniques. Another important idea is where to add noise, right? So that in general, the key to achieving differential privacy or some of these other definitions is to somehow inject noise into the system. And you can do it at various places. So you can do it on the input. So we saw things like randomized response, where you take the actual bits of the input and you flip them in this probabilistic way. You can do it on the output. So we saw things like the Laplace mechanism that you apply any function to the data, add noise to it afterwards. Or some of the techniques in machine learning where you basically do the machine learning, you do the empirical risk minimization, you get out the final weights of your model, and then you add noise to those weights. But you can also do it on some intermediate results, right? So one example of that was with the machine learning technique. Rather than add noise to the sort of final coefficients of the model that you're fitting to the data, you can actually add noise to the gradient and then basically do sort of standard stochastic gradient descent, but you're adding a little bit of noise to the gradient, and so you'll find possibly a different solution that you would get without privacy, but that is one way of injecting noise and ensuring that you satisfy privacy. And there isn't sort of an easy answer about sort of where the best place is to inject noise. It really does depend on the problem. But ideally, you're sort of looking for some kind of information bottleneck. So some place where for the analysis task that you care about, you can kind of summarize the relevant information as concisely and compactly as possible. So if you think about from a statistics perspective, like the notion of sufficient statistics, for a particular model that I want to fit, if these are the sufficient statistics for that model, then I could try to add noise to those, and then I can do whatever I want with the noisy statistics afterwards. And of course, related to that is reasoning about sensitivity. So some of the real challenges with the work on stochastic gradient descent is thinking really carefully about sensitivity, because those algorithms are quite complicated, and thinking about how one person's record could affect the final output actually requires some fairly deep thinking. Okay. And of course, the other aspect is that where you inject the noise might be dictated by the application. So with Google's Rapport, right, they really didn't want to collect the data. They didn't view themselves as sort of a trusted data collector. They wanted to, in this particular setting, they wanted to add noise locally to each individual person's data, and then send that data to Google after the noise has been added and it's basically safe to release. Okay, a few more ideas. So this notion that I'm just calling loosely lossy transformations, but the basic idea is that you have some analysis task and you're going to kind of accept some error in your analysis in order to achieve a better privacy utility trade-off. So I mentioned when we were talking about query answering over tabular data, when you're building histograms, you can do data adaptive binning. So if you have regions of your histogram that are very sparse, like let's say there's no data in that region, you can build bigger histogram bins that simply summarize that region and end up giving you better accuracy. With Rapport, right, they wanted to know the most frequently set home pages, but rather than add noise to the set of all possible home pages, they did this compression down using a Bloom filter, which of course created some potential collisions and loss of information, but they were able to get a much better privacy utility trade-off. And with social networks, we saw imposing some restrictions on the degree of the nodes in the graph, again, allowed you to get a more accurate result. But with all these, you're making an implicit bias variance trade-off. So you're sort of systematically injecting some bias into the results that you're producing at the expense of lowering the variance, the noise that you have to add. And that's a trade-off that can be difficult to calibrate. And one thing that can be very helpful is to leverage domain knowledge. So with a lot of these different techniques, the designers of the algorithms took advantage of sort of background knowledge about the kind of typical properties of the data, right? So with On the Map, they had previously published, this is something that Ashwin didn't describe in great detail, but they had previously published data, and so they had some sense of the sort of typical structure, and they could do some kind of clustering beforehand to reduce the noise they had to add. With the Rapport task, right, they expected there were going to be some heavy hitters, some websites that were quite commonly set as the homepage, and really that's what they were after. They weren't interested in the long tail of web pages that were not often set as homepages. They were really interested in the heavy hitters. And with the other applications, they leveraged domain knowledge as well. And then the fifth kind of cross-cutting idea is that the privacy definition that you come up with may necessarily have to be application specific, right? So differential privacy on the one hand is it's a very general definition and it's a very robust definition. But it really, as Ashwin illustrated by looking at it through the lens of pufferfish, it's really protecting individual records, so viewing a kind of record as a secret, under some assumptions about sort of the data generating process that produced those records. And that may not align with the semantics of your application. So we saw applications where one person's data wasn't easily encapsulated into a single record, right? In trajectory data, one person can contribute multiple data points to a trajectory. So with the social network, one person's data, you can think about it as spread across multiple edges in the network. So really, to apply these techniques to your application, you need to think carefully about what are the secrets that you're actually trying to protect, and then who are the adversaries? So what sort of model of how the data is generated can they leverage as prior information, and what data correlations can they exploit? And that will help you, say, tailor a pufferfish privacy guarantee to a specific application. Okay, lastly, I thought I could mention three challenges, okay? So the first challenge is moving from prototypes to real-world deployments. Okay, so I would, and this is maybe me opining about some of the directions that I think would be interesting to head. So I think that the research community would really benefit from seeing more examples of real-world deployments and actually engaging in the development of real-world deployments. So we've seen a few. Ashwin mentioned the Census and Chrome and the Chrome browser. There have been a few others that he mentioned. These real-world applications really demonstrate that differential privacy can be used in a real-world application. And they also raise really important research problems. So once you actually sit down to try to embed this into a real-world system, all sorts of other issues arise. So to give you one example, so you might worry about side channel attacks. So somebody actually having knowledge of how the algorithm works and possibly finding some other mechanism for attacking the data. And in fact, there was a paper a few years ago that showed that the Laplace mechanism, so the thing that we've been talking about and that is used in a lot of different algorithms, because Laplace noise is generated using floating on a computer, so using floating point computation, there are some sort of particularities about how it's generated that you can actually seeing the answer and looking at some of the least significant digits, you can actually sometimes reconstruct exactly how much noise was added and then recover the true answer. So it's an example of a side channel attack. And there are ways to circumvent that by using a different random number generator. But considering those things show up when you actually think about trying to deploy these things in the real world. And of course, as I mentioned before, matching the formal privacy guarantees to the particular needs of the application. So Ashwin mentioned the census work that'll be talked about on Thursday, where you've got employers and employees. Employers have secrets they want to protect, employees have secrets that they want to protect, and actually working with stakeholders to identify what those secrets are and what's important to protect and what can be disclosed is really important in actually deploying these things in the real world. So a second challenge is to move from these kind of one-off algorithms to actual systems, so differentially private systems. And I would say that today I think differential privacy can work in the real world, but it requires effort and it often requires sort of consulting with a team of differentially private experts to kind of put together the right algorithms and make the right trade-offs to design a good system. And in some ways it resembles the early days of database research. So you all are database researchers and know the sort of history of the development of the relational data model and query optimization. So here's a quote from Codd in the 70s where he said, database systems at the time, right, were without exception ad hoc, cumbersome, and difficult to use. They could really only be used by people having highly specialized technical skills. Right? And what we saw in the database community is the development of the relational model and useful abstractions, such as the relational algebra and then query optimization, that allowed end users to actually just think in terms of SQL and have a system automatically compile that down to highly efficient, scalable code, right? And so I think we need to move in that direction within the differential privacy community, rather than sort of one-off algorithms. So you can think of like one-off join algorithms to whole systems that allow you to compose these different techniques in different ways and build up more complicated analysis systems. So there has been some work on kind of thinking about differential privacy from a systems perspective. So there's a paper at SIGMOD in 2010 on privacy integrated queries. And the basic idea was to kind of create a thin layer around the database that would provide some privacy protection. And you could do various data transformations, such as selecting tuples, joining two tables together, doing a group by, and so on, projecting out columns you don't care about, and so on. The nice feature of Pink is that it guaranteed whatever program you wrote satisfied differential privacy. Okay, so you could do a combination of joins and filters and projections, then take a noisy count, and it would do the appropriate sort of calculus to make sure that the noise that was added was enough to ensure differential privacy. But it was up to you, the author of the program, to actually ensure that the output you got was reasonable, right? So you could, with Pink, you can very easily write a program where the amount of noise that you have to add is huge, and you get lousy results, right? So what we really need is not just sort of a system that safeguards people from accidentally writing something that violates privacy, but actually a system that has modular components and allows for the opportunity for automatic optimization, right? So I could ideally declaratively specify, here's the analysis task I want to do, and the system itself could figure out which are the best components to substitute in to carry out that analysis task, much like a query optimizer works today in modern database systems. Okay, and the third and final challenge is around communicating privacy utility trade-offs. Okay, so with any system, as we've seen, there are some sort of fundamental limits and inherent privacy utility trade-offs, right? So you're inevitably going to sacrifice some accuracy in the statistics or quantities that you are extracting from the data for the sake of privacy. And it's necessary to communicate these to the stakeholders, right? So with applications, say at the Census Bureau, talking with how the statistics that they release are used, what's important to release, which statistics can tolerate error, which ones have to be released exactly. There are very important conversations to have there about sort of the privacy utility trade-off. And so there was some work that Ashwin and I did with some collaborators that appeared at SIGMOD last year on DPComp. And it's actually a public website. You can go and check it out. And it attempts to communicate to some extent some of these privacy utility trade-offs by showing a bunch of different algorithms and on example data sets. So these are non-sensitive, publicly available data sets, but comparing the different algorithms with each other and then trying to give the end user some sense of their overall sort of practical usefulness on some realistic data sets. And one of the things that we found is just actually this raised all sorts of interesting questions, like, if you're going to visualize data that's been perturbed for differential privacy, there's a lot of questions around what's the right visualization and how do you communicate to the user that this data has been perturbed and there's noise added, so they understand that needs to be factored into their thinking about the data. And ultimately, we really need algorithms that are tunable, right? So you need to be able to not only communicate the privacy utility trade-offs to the end stakeholders, but actually design algorithms that effectively have knobs, right? So that you can say, okay, for this task, it's really important that you preserve these qualities about the data, but I'm willing to have slightly less accuracy on these other qualities, and have the algorithm kind of automatically reason with those priorities and preferences and designing an effective solution. And with that, I will say thank you for listening, and I'm happy to take any questions, or if you have any questions for Ashwin or Shi. Okay, well, we're around after the break, so if you have any questions, you can come find us offline. So thank you very much.